In this video, we want to take a look at some miscellaneous topics about circuits. We want to talk about power in circuits, internal resistance of batteries, and a little bit about using voltmeters and ammeters. I'm actually going to start with talking about voltmeters and ammeters and then go to power and internal resistance. So voltmeters and ammeters. Again, an ammeter is an object you put in a circuit, this device that's made to measure current. Whereas a voltmeter measures the delta V. Okay, important to recognize it's measuring the change in potential from one spot to another. So if I want to use an ammeter, the symbol in a circuit is an A in a circle. Symbol for a voltmeter, V in a circle. Okay, so the key thing to know about an ammeter is let's say that we have a little circuit. We're going to put a battery. We'll go ahead, we'll put some resistors in, waka, 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 right? Sure, another resistor in, waka, 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 waka. Like so. All right, and so the question is, we want to go ahead and measure some current with an ammeter. So if I'm going to hook my ammeter up, you say, well, let's say that my goal is to find the current that's flowing through resistor 1. Then you say, well, how am I going to hook up my ammeter? Here are two options. One option is I hook up my ammeter like so that I'm making a connection on either side of the resistor. Option number 2, I go ahead and I hook my ammeter up here. Option 3, I hook my ammeter up over here. So the question is, what's the best way to hook up the ammeter? So the answer, of course, is that an ammeter is made to measure current, which means I need the current to flow through the meter in order to measure it, right? It's going to measure how much is flowing through it, right? And so you say, the key thing about any time you take a measurement is you want to alter the thing that you're measuring as little as possible. In taking the measurement, you don't want to screw up the thing you're trying to take the value of. So let's talk about what would happen here. What the little bit of extra information that you kind of need to have about an ammeter then is you say, well, I don't want to change the value of the thing I'm measuring, the current flowing through. So here's the question. If I had the world's best ammeter, would that ammeter have high resistance or low resistance? Well, if I have high resistance, it makes it more difficult for charge to flow. And when I hook the ammeter into the circuit, it would slow down the rate of flow. We don't want that. And so an ideal ammeter has zero resistance. Is an ammeter really going to have zero resistance? No, but ideally it has very, 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 very small one. So here's what happens. If I go ahead and I hook my ammeter up like this, and I put the ammeter here, then my current's going to flow in. Here comes the current out of the battery. And when it gets to this junction, right, then it would have a choice, wouldn't it? Some of the current would flow this way, and some of the current would flow this way, right? My current would split. So would I be measuring all the current? You say, no, I'd just be measuring how much goes this way. But there's a problem. Because the ammeter has very, very tiny resistance, we'll say we can treat it as if it had zero resistance. When the current gets to here, you say all of this wire and then all this wire, if there's no resistance, there's no delta V from here to here. So all of this would be at the same V level, wouldn't it? Because there'd be nothing taking energy out of the charges. And gosh, if I have the same V level on either side of that resistor, then there's no E field through that resistor. There's nothing to push the charges through. The charges would just flow around it. I would have provided a shortcut for charges to get from one side to the other side of that resistor. And so charge will just flow around like this, and nothing will flow through that resistor. This has definitely changed the way this circuit operates by hooking that ammeter up like that. Hooking ammeter in parallel, right? So charge comes in, it would have a choice, this or this. Well, it's because of zero resistance, it's all going to flow that way. And I wouldn't get flow through this. So I've altered the circuit as a whole. The circuit as a whole, before I hook the meter in, you say current would have to go through this resistor and that resistor. Together, they're going to slow down the rate at which charge can flow. And I would have a certain amount of current. If suddenly I short circuit past this thing's no longer slowing things down. I'll get much more flow than I should get, right? I've changed the resistance of the circuit. I've taken this guy out effectively of the circuit to provide a path to get around it. And so that will really alter the circuit and screw things up. In reality, if you did this, you'd have more current going through this guy than it's supposed to. And so this guy would drain a lot more power. Things could overheat, could cause fires, cause all kinds of problems. Doing something like this, hooking your ammeter up, you'll be running more current through the ammeter than we were expecting. You could blow the meter. So you say ammeters, we always attach in series. And I think that this one just kind of makes sense. If I'm trying to find the current flowing through this, I'm going to hook the ammeter up in series with it so that whatever flows through the meter is what's going to flow through the resistor, which is what we want to know, how much goes to the resistor. Because this has a very, very tiny resistance, it doesn't really alter the flow of the current in the circuit very much. And so life is good. What would happen if we put the ammeter here instead? Well, whatever went through the resistor would go through the meter. Again, it's going to be the same. It doesn't matter whether you put it before or after that resistor. You're going to measure the same amount of current, same amount of flow going through it. So we always hook ammeters up in series with the object that we're trying to find the current through. And this, now, something you should be aware of is the fact that a real ammeter has a little resistance. And so when I hook the ammeter into the circuit, it's going to then cause the current to actually decrease a little bit. The thing is trying to measure. So the error, right, in what the circuit was doing before I hooked the ammeter in versus after is going to cause a little bit of error in that way. You should be acquainted with that idea, right? But that's ammeters. A voltmeter is meant to measure delta V, the potential difference. And so when you have your voltmeter, right, you've got your two probes, right? Actually, I'm using a multimeter here, right? It can measure multiple different things. This object can do calculations for potential difference, right? It can measure currents, and it can measure resistances. But say we're going to go ahead and use this to measure delta V, right? We might set our dial over there. And you say, I've got the two probes, two spots. I'm going to hook this into the circuit. And so since I'm just trying to measure delta V, I want to find the change in potential between two locations. So when I hook it up, I would just touch the wire, I touch into the current here and here, right? So like I'm hooking it up, brink, brink, to either side. Now what this means is I'm wiring that meter in like so. See, I'm trying to find the delta V for this resistor. For R2 here, I would hook my voltmeter up like so. And so what this is going to do is my job with the voltmeter, again, I want to affect the circuit as little as possible, right? And so what I want to do is I want to measure the V value here and measure the V value here and take the difference between them. So what I want is I want my meter to just taste the charges on this side. Just kind of, and taste the charges on this side, and see the difference in the V between the two sides. I don't want to alter the current. I don't want to alter the circuit. And so that means an ideal voltmeter. What's the resistance going to be like for an ideal voltmeter? Do I want it to have little resistance or a lot of resistance? Well, my goal is to not change the circuit. I want everything to act as if the meter wasn't there. And so when the current comes in, I want it to just keep going through the circuit the way it was. I want just a teeny little bit to go through the voltmeter so I can measure the V value here and here, right? Just tasting the V value. And so that means an ideal voltmeter would have an infinite resistance, all right? Okay, is something going to have an infinite resistance? You say no, but it has a very, very high resistance. Voltmeters have a huge resistor like built into them called a shunt resistor, built in that's going to prevent make it so that just a little teeny trickle of current will flow through the meter. And so the circuit will act pretty much as if that voltmeter wasn't there, right? So I'm just measuring on either side. What would happen if I hooked my voltmeter up in series with the thing I'm trying to measure the resistance of? Well, that voltmeter, remember, it has a huge resistance built into it. So what happened to the circuit, if I go ahead and I hook that voltmeter in, is it would like kill the flow of charge in that circuit, right? And the current, the whole circuit would like slow way down as it tries to make its way through this huge resistor. And so like these guys then suddenly we get almost no current through them, and they'd be drawing very little power. And like basically, if these were light bulbs, they'd probably go out. That would like basically block the flow of current through that pretty much, if I hooked up in series by accident. So voltmeters, remembering that we're trying to measure the delta V, the change between two spots, means we're going to go and touch to the two spots. We're going to be hooking it up in parallel, right? So we attach in parallel with the thing that we're trying to find the delta V across. Ammeters, we're trying to measure flow. We need all the flow to go through the meter, so it gets wired into the circuit. When you hook up an ammeter, you have to break the circuit and hook in the meter, right? A voltmeter, delta V's are easy to measure. You just go ahead and just touch to the wire, bink, bink, and get your delta V, right? You don't have to like rewire the circuit at all. So that's what you know about voltmeters and ammeters. Recognize that when I hook a voltmeter up, it is going to affect things a little bit because technically a teeny little bit of current goes this way. When you wire things in parallel, right? Remember, there's a resistor in here. Resistors in parallel. What effect that has is it reduces the resistance of that part of the circuit. The total resistance gets less. It's a little easier for chargers to make their way through if they have a choice of two paths and they kind of split up a little bit. They're not jammed together quite as tight. Then you get a little more current through. And so it's going to actually lower the resistance of the circuit as a whole. That would be like the error that it would cause when you wire in the voltmeter. So it would lower that total resistance a little bit. So anyway, voltmeters and ammeters, that's what you need to know about them and be able to think about the error that they'll introduce when you hook them into your circuit. Power in electrical circuits. So you'll recall that power, we use the symbol capital P for, right? And do you remember what power is back from the energy unit? We say it's the rate at which energy is transferred from or converted from one form to another. So we think of power, right, as being the change in energy or change in time. If I did that, that would be my average power. If I want an instantaneous power, we said that power would actually be, it's a rate, it's going to be d energy dt, right? So I'm just going to think about it this way. It's a little easier to talk about. So it's my change in energy over change in time. And so you say, if I think about this as being, my energy transferred or energy converted or energy transformed per time, I'd like to talk about this in terms of circuits now. In particular, what I'm going to do is we're going to calculate a power rating for a battery, for a resistor. So we're thinking about how quickly energy is being converted into heat in that resistor. Okay, that's specifically what we're going to calculate here today. And so you say, well, if I do that, I want to have energy per time. And so you say, well, thinking about what we know about circuits, we've been using Ohm's law. I'd like to get a power in terms of these different circuit variables, these things that I can measure on a multimeter, right? Okay, so I can figure out like how quickly energy is being converted in this object. So if I want to get time in my calculation, which of these variables has something to do with time? You say, oh, wait a minute. Yeah, I remember current, right? Isn't it true that current is my charge per time, right? flowing through something, right? Flowing through a spot. I go look at my wire and I look how much charge goes through each second. And so if I go ahead and say, okay, well, my power then, we're going to say, we'll go ahead and we'll put the current into our calculation, right? You say, well, then I'd be putting in charge per time. You say, okay, I got that part. Now I need energy. So you say, which one of these variables has to deal with energy? And if you think about that, you'll say, oh yeah, delta V, you remember that's my delta UE per Q. That's my change in energy, right? Per charge. And so if I go ahead and I put the delta V in there, that's my change in energy per charge. And you say, hang on a second. Charge. This is what I need, the change in energy per time, which is what I was shooting for, right? You say, sure enough, this is going to be a formula for power. So power is just going to be the current times the delta V, which kind of makes sense. You say, hey, delta V, that's my change in energy for every unit of charge that goes through. And this is how many of those units go through each second. So that's just going to be my change in energy per second, which is what I want, right? That's my power. We can go ahead and we can write this equation now in a couple different ways if we'd like. We can go ahead and substitute in using Ohm's law. You see how delta V is I times R? So where it says delta V, I could put in IR. And so then this would just be I times IR, or I squared R, would be my power, right? I can, of course, substitute in another way, right? You can say, oh, wait a minute. I can get rid of the I this time. You can say I would be delta V over R. And so if I put in delta V over R, I'll have delta V times delta V over R. So this will be my potential difference squared divided by the resistance. And so here's three different ways of writing the power rating for a resistor in a circuit. So that's specifically what this is for resistance. And so, again, what are the units for power again? Do you remember that we said that power is energy per time? And so we'd say the units were joules of energy per second. But I, of course, can rewrite this if I want, because we give the special name, a joule per second is called a watt, right? Okay. And so electrical power is measured in watts, right? Which is not a surprise to you. The other comment I would make about this is don't forget that the actual formula looks like this. Power is change in energy per time. So if I have a power rating for something and I want to find out how much energy has been transferred, I can rearrange this. I can, differentiate it. And you say, hey, rearranging this, you say, I would have D energy equals power dt, and then I'll just integrate, right? And so the change in energy is just my integral of power dt. It is a relationship to be aware of, right? And you say on a graph, if I had the energy that's been transferred, the power rating, oh my gosh, my power rating versus time, then the area under that graph is going to be the energy transferred. Okay, so internal resistance for a battery. So let's say I'm going to go ahead and I'm going to hook up a battery in a circuit. Okay, so here I'm going to draw the big battery, okay, to kind of emphasize something here, okay, instead of just using the circuit symbol. So here is my big battery with its high V side and its low V side, right? And say I'm going to go ahead and hook this up. Here's my wire, right? Here I'm going to put a switch in, okay? So I can turn the circuit on and off. Here we'll have some other external resistance. Maybe this is a light bulb. Maybe this is a little flashlight, right? And this talking about my battery and my flashlight. I'm going to go ahead and hook in like that, okay? And So I want to go ahead and think about what's going to happen here. Well, you know that the ends of a battery, right, are sometimes called the terminals of a battery. Okay. And so what I want to talk about here is the voltage that I'll read on that battery. If I go ahead and I hook up a voltmeter, right, and I touch it to the one terminal, and I touch the battery to the voltmeter to the other terminal, then what this voltmeter is going to read is called the terminal voltage. That's just the delta V of the battery. Okay. All right. Is what that's going to register. However, interestingly, when I close the switch and I turn the circuit on, that delta V reading is going to change. You're saying, wait, what? Though the battery is currently running or not running is going to change the delta V of the battery. You're like, wait, I thought the whole thing with batteries was to provide a constant delta V. You know, what's going on here? Well, here's the deal. All right. You know that if you run a circuit for a while, the wires heat up. They get hot, right? That's because of the resistance in the wires. Charges are trying to make their way through. As they do, they have to collide into impurities in the metal and discontinuities in the crystal structure and such. They're going to bounce off boundaries and stuff between crystals and stuff. It's going to slow them down. And as they slam into these particles, these atoms in the wire, they're going to make the atoms in the wire wiggle and jiggle more. They're going to cause heat, thermal energy, right? They're going to lose some energy going through resistors. So you say the wire gets hot because of that. But now my question is, hey, what about the battery itself in a circuit? What happens to that battery as you run the circuit? Doesn't the battery heat up too? So you know what that means? That means the battery has some resistance built into it. Okay, what we call internal resistance. Okay, just the materials, the metals and stuff the battery's made out of, they have resistance in them. And so that means that while there is a certain delta V value for those two metals, the two terminals of the two electrodes in the battery, right? You know, my two metals that make a delta V, that how the voltage gets created. That's not necessarily going to be the delta V you measure on that battery when you measure the terminal voltage. You won't necessarily get that ideal voltage of those two metals. It'll be off a little bit because of the internal resistance. So what I'm going to do is I'm going to diagram this idea that there's a little bit of resistance built into the battery. I'm going to diagram that like this. Look, here's my one side of the battery, and look, see this? Right? And I can imagine that inside the battery, there's a little bit of resistance built in, right? That's just part of the metals, right? Part of the battery itself. This internal resistance will symbolize with a lowercase r usually, right? To kind of realize there's a little bit of resistance built into the battery. If I could somehow get rid of that internal resistance, then the delta V I would measure here would just be the delta V for the two metals. Okay, that idealized delta V, that idealized voltage or potential difference for the two metals, we sometimes give that the symbol kind of curly E there, right? This kind of script E. Okay, that script E is we call that the EMF for the battery. Okay, EMF is this unfortunately poorly named thing. One of my profs in college thought that it was had to do with translation in and out of one language to another, that it accidentally got mistranslated. I don't know if that's true. I think it's just poorly named. It's called electromotive force. Most people just call it the EMF because it's a little bit shorter to say than electromotive force. They give this symbol script E. What is it? It's just the idealized delta V. Okay, for the battery. So a lot of times in circuits, they'll go ahead and they'll have this script EMF symbol next to the battery to tell you, oh, that's the voltage of the battery. Okay, that's the idealized one. All right, so here's what's going to happen. If I have this circuit and I have it turned on, I close the switch, right? Then what we're going to have is we'll have I'll be measuring the closed circuit voltage for the battery. Okay. That's turned on. Okay. And so current is flowing. If I measure that, what's going to happen? Current's going to flow, right, through the battery. It's going to flow through this resistor, right? Yeah, I'll have this current. You say, but wait a minute. When charges go through a resistor, they lose energy, don't they? And so that means my change in potential that I would measure between here and here is not the same as the change in potential between here and here. Do you see what I'm saying? I go up voltage to the battery, but then I'm going to go down voltage because of the resistance in the battery. And so when I'm going to measure my closed circuit voltage, right, that delta V for closed circuit, I don't know, closed circuit, CC? Sure, why not? You say that's going to be not just the EMF of the battery, it's going to be minus the current flowing through the battery times that internal resistance. Because I'm going to lose some energy per charge going through this. So the change in energy per charge, the delta V here that I measure, that terminal voltage for closed circuit will be that. On the other hand, if I had open circuit voltage, right? This is when the circuit is turned off, right? And so the switch is open, right? That means the circuit's turned off. So open the switch, charge can't flow through. Make sense? Okay. So if it's turned off, current is not flowing. And so what that means is that we're going to let the charges are going to be able to rearrange themselves in the metal until they get to equilibrium, right? The whole thing with the way circuits usually work, you remember, is you got the two terminals, right? The two electrodes, and there's a chemical reaction where charges are trying to move. Electrons go from low V to high V, right? Electrons trying to move in there. And the problem is that would charge up the terminals. So we have the electrolytic solution there with the ions that can migrate and can keep the things neutral. So charge keeps flowing. It keeps trying to get to equilibrium, but we keep pulling out the rug from under them. And so the charges can't build up, so it can't get to equilibrium. Well, now we're going to let it get to equilibrium because I've broken that circuit outside here. And so if the charges rearrange themselves here, so that an electrode charge will teeny little bit of charge build up on the wire, so that now there is no delta V, right? Is the idea. There's no current flowing, rather. Charges can rearrange themselves here so that it's in equilibrium. So I'll have just the two different metals with different delta Vs. When I hook in my actual voltmeter here, right? Remember, this has a huge resistance. There's hardly any current flowing at all. It's really just taking a taste here. So this gets to equilibrium. So, let's just say, basically, I'm going to just be measuring the delta V here. If there's practically no current flowing through this, no current through this resistor means essentially, like I said, it gets to equilibrium on either side of the resistor. So there's no delta V there. And so this is just at the V value of the high side of the EMF, and then here's a low side. So I just measure the EMF. So that is just going to be my delta V for open circuit voltage is just going to be the EMF of the battery. Okay, that idealized voltage of the battery. So there's a couple of side effects of this. One is if you have batteries and like say, oh, I'm running around, I want to check and see if these batteries are dead or not. Let's check what the voltage is on the batteries. And I go and I touch them to the battery. It'll say, oh, yeah, it's working like a champ, right? Sometimes. But then when you hook it into the circuit, there's a whole ton of resistance that's built up because it's like oxidized and corroded and stuff inside my battery, right? And then when I actually put it in, so it seems fine, but when I actually hook it in, this resistance here keeps charge from being able to flow very well. And so like over time, like it builds up. But then when I put in a circuit, all of a sudden, pew, if I measure the open circuit voltage, I get like practically no voltage, this dead battery. So that's one little irritating thing about that is that measure the voltage of a battery doesn't necessarily tell you how good a shape that battery is in. The other effect, all right, is if my battery, right, and you say there's this little, and you say, usually what you would expect to happen here, I'm going to make a little circuit, okay? And say for this circuit, we're going to have waka, 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 right? Waka, waka, waka. Here we go, right? I forgot to put my switch in. Look, there's my switch. Okay. Here's my battery, right? And you say, okay, there's a certain amount of resistance in this circuit. I've got these two resistors, right? And so what you would, if you go ahead and you calculate this out, you say, if I've got these two resistors in parallel here, say R1 and R2, you say, so when the charges flow down the wire, they get to here and you say, gosh, there's these two resistors, and together they're going to make a resistance that's smaller than either of them would be by themselves, right? Because they're both paths there, it's a little easier for charges to get through. They can kind of split up between them. They don't have to all jam through this guy or all jam through this guy. And so the resistance goes down. And so you would say, well, gosh, what'll happen if I go ahead and I got rid of this one, right? So I should have put another switch in here is what I should have done, right? Say I flip open this switch, this resistor goes away. Now there's just this resistor, right? Okay, and so the total resistance actually goes up, right? You know what? I'm going to redo this. I'm going to take my white out, and I'm going to change this so that I have a switch where I want it, and it looks like a switch, right? Instead of there it is. Oh, this whiteout is trashed. Seriously? Son of a bitch. Fuck. I don't want to have to buy more whiteout. Have I got whiteout in my drawer here? I do. Look, I got a brand new package of whiteout in my drawer. Oh, that's awesome. Okay. Hope it works well. Okay, so an effect of internal resistance on a circuit. Say that I hook up a circuit like this, and I've got my battery, and I've got two resistors like this. I went ahead and have a switch here, so I can turn my whole circuit on and off. And here, what I'm going to do is start with this circuit open, this open here, okay? And if I go ahead and close the switch, current is going to flow around, right? My current's going to flow out of my battery. It's going to flow this way. It's going to flow through R2 and then back again, right? And back to the battery, right? And so I have my circuit running like this. And you say, so right now I have this resistance R2, I feel, right? And I think that that's all I've got. And so if I went ahead and I hooked up and I hooked up a voltmeter and say I want to measure the delta V from here to here, right? Then in an idealized situation, right, this circuit's open here, so there's no current flowing through this branch. They can't flow through, the circuit's broken. So I would just have current flowing like this. I'd have, look, there's a delta V from one side to the other, this EMF, one side to the other of the battery. You say, as I go around a loop, when I end up back where I started by Kirchhoff's loop law, I better have a total delta V of 0. I'd be back to the starting V value, right? I go up through the battery and I go down going through the resistor and I'm back where I started again, right? So whatever the EMF is here, I'd have to go down that much here, right? Okay. And so ideally then you say, well, what happens if now I close this switch? Let's say those two resistors are identical. R1 and R2 are the same size. Then you say, well, gosh, that would, when I put them in parallel, right? If I've got my total resistance, you say 1 over R parallel, that's 1 over R1 plus 1 over R2. And again, if these R's are the same size, you'd say what's the same denominator? It's just going to be, that would give me 2 over that R value, right? And if I flip them both, you get, hey, look, R parallel is that R that originally had over 2. So I'd have half the resistance. And so you say, well, gosh, delta V is IR. And so you say, gosh, if I just went ahead and still, if I have the resistance, right, I would like double the amount of current that's flowing into this region, right? Okay. And that's what you're expecting to find, right? Okay. And you say the delta V here should be the same as it was before because still charge comes in, up delta V the battery, and it goes through both of these, right? You see, but still my delta V from here to here. Then I got to be back down to this bottom side. It's still going to be the EMF, right? That's what you expect. But what we don't realize, right? So we're expecting like the current here being drawn out of the battery to double, right? Because I've halved the resistance, right? So we're going to expect to see my new I, right? It's the same delta V from the battery, right? And you say, I do I times R, but my new R, I have now just cut in half. And so you're like, oh, well, the same voltage from the battery is about to be double the current, right? And so if I put an ammeter here, you'd expect to measure that current flowing through would be doubled, right? But that's not what happens in real life with a real battery, because the real battery has some internal resistance built into it, doesn't it? Right? So there's a little bit of resistance there. And so what that means is the delta V here isn't actually going to be equal to the EMF of the battery, right? Because I've already taken a little bit of energy out of the charges here, right? The voltage dropped here already some. So when I go ahead and I close the switch on this second one, right? The voltage here, you would expect, we're expecting the voltage to stay the same, right? But because of that internal resistance, it doesn't. The total resistance of the circuit isn't actually having, just the resistance in this part halves. Do you see what I'm saying? And so I'm going to end up getting a different value out than I was anticipating because of that internal resistance of the battery, right? And we could calculate that out if we're interested. But there's a section in your textbook where Fletcher talks about this. I think it's called Exotica Real Life Light Bulbs or something like that, where he talks about this idea. The other thing that, while we're on it, the other thing we should talk about is with circuits. Again, we talked about, I think I mentioned this before, that over time, as the circuit heats up, the resistances change, and so that'll change the delta V values places and the currents places, which is something else awkward that can happen in real circuits. But just pointing out, don't forget, in real life, there's a little bit of resistance there, and that's going to affect how things happen, kind of downstream here in the rest of the circuit. So in this case, if I go ahead and I close this switch, right, we would be expecting this voltage to stay the same, but it's not, because there's a potential difference from here to here and a potential difference from here to here, right? But let's just say, throw some numbers in there. Sure, why not? Let's say that little r was, I don't know, you want to say that's 2 ohms? And say that these r's are, I don't know, I'm trying to come up with a number that's going to be reasonable. I'm just going to use 10. Say these are both 10 ohms. And let's say that the voltage of the battery, let's say that EMF, that idealized EMF, let's say that was something that divides, 24 volts. Okay. Then if I look at my circuit, you'd say delta V is IR. This is before I close this switch, okay? Then I just have this resistor and this resistor, right? And so you say, okay, well, I would have, these numbers are going to come out awkward when I close the switch. I'd have, it'd go through a 2 ohm resistor and then through a 10 ohm resistor and then back around. So the total resistance is actually 12 ohms, right? And the delta V is 24 for going from here around to here, right? I'm going to go up 24 here. I got to go down 24. So my current is going to be 2 amps. When I close the switch, if it wasn't for this, I'd be expecting, like I said, my delta V here, I'm expecting to be the same, right? You know what I mean? It was like, oh, if this wasn't there, right? Whether it's closed or not, I still got to go up 24, got to go down 24, right? But I'm not really going down the full 24 here. I'm only going down, what's the delta V here? Now that we know the current is 2 amps that flows in, before I close the switch, I'm going to have 2 amps going through 10 ohms. I'll have 20 volts here, and then 2 amps flowing through 2 ohms, 4 volts here. So I would drop down 4 volts. This is before, and then this would be 20 volts. So what I'm anticipating, if I'm not thinking about this, I think that the EMF is 20 volts because that's what I'm measuring here, right? If I'm not thinking about the internal resistance. And I'm like, oh, when I close this switch, I'm going to have the resistance, right? And so I'll end up with the same delta V, but half the resistance, you'd expect. And so you say, well, gosh, same delta V, but half the resistance. I'm expecting to have double the current flowing, right? And so from 2 amps, I'm expecting to go up to 4 amps. But that's not what happens. You say, doing that calculation, you say, "10 ohm and 10 ohm in parallel. When I close the switch, the resistance for this part is going to be half, right? So the resistance for this part would be 5 ohms, right? If I did that, I would do here. We'll do it out. You say 1 over R parallel is going to be 1 over 10 plus 1 over 10, right? Which would be 2 over 10. But that's 1 over RP. Flip it, 10 over 2. You find that R parallel would be just 5 ohms. So 5 ohms. So I like to put in a circle right there in the center there so I remember that region is 5 ohms. So you say, well, now I've turned this into 5 ohms. You say, but look, this is still 2 ohms. I go through 2 ohms and then I go through 5 ohms. You're like, gosh, that's a total resistance of 7 ohms, right? And so total resistance is 7 ohms. You're saying my volts going up from here to here, right? From here to here, it's still got to be 24 volts, right? For that battery, the EMF, right? But you say it's going to be my current times the total resistance of 7. And so now my current, instead of the current being doubled, right, from 2 to 4, my actual current is going to be what? 24/7 amps. You see, 24/7, that's more. It's going to be what? There's like 3 3/7 amps. He said I was expecting the current to double because I'm having the resistance when I add that in, but that's forgetting the resistance there. So instead of getting 4 amps, I'm only getting 3 3/7 amps, and that would like confuse me if I was not aware that there's that internal resistance in the battery. So things won't operate quite like I was expecting because there's resistance built in there. So just something to be aware of. This is like something that normally. Well, I'll just tell you from my own experience. I've tried to do this as a demonstration, right? Can you imagine trying to show students, oh, well, when you hook this in, it's actually going to bring more current, more current through. So here, check it out. But the light bulbs, you would naively think if this wasn't here, you'd say it'd still be the same delta V. So this bulb would still get as much energy. It'd still be just as bright, right? And so you'd say, if these were light bulbs, and you'd say, well, gosh, then when I add this in, the brightness of the sky shouldn't change, you would say, right? It would just be, I'd just be adding another light bulb that's just as bright, twice as much current drawing, lighting 2 bulbs instead of 1, right? But what actually happens is you get less current, right? Because instead of having 2 amps going through this guy, now these are identical. It's going to split the current evenly. I'm going to have half of 3 3/7. So this bulb actually gets a little dimmer. Right? There's not quite as much charge per second flowing through lighting up the bulb. So like you hook this in and all of a sudden they get dimmer and you're like, oh, that's not what was supposed to happen. But it's because of that internal resistance there. Gosh, I babbled quite a bit on this. But that's just what I want you to recognize is that, there is effects of having that internal resistance in a battery. Now, there's one last thing about this I want to say before I wrap this video, and that is if I go ahead and I think about a circuit and I say there's this one little thing that's on like the objectives list for AP physics and it's saying, hey, batteries. So here's like, here's my battery, right? Right? Inside that battery, there's a little bit of resistance, that internal resistance, right? Outside the battery, let's just call this total resistance outside of the battery, right? Yeah, I'm just going to draw this over here, right? Right. Internal resistance, right? Outside the battery, there's some resistance out here. Okay. This outside resistance, here's my internal resistance. Sometimes the resistance that you're hooking the battery, the voltage source up to, here we've got the EMF built in. But sometimes that resistance you're hooking up to out here is called the load for the circuit. Okay. All right. Is the resistance that battery is having to fight against to push charge around. Okay. And then, of course, my internal resistance. So the question that pops up on the list of AP things you're supposed to know, and have I seen this show up on an AP exam before? Yeah, I think it showed up once. But the question is, I'm going to draw current out of this battery, right? When I hook it up like this, current's going to try to flow out through that resistance. The size of the load that I put will affect how much current I can draw out of the battery, right? Which will have to do with how quickly I am draining that battery, the power rating of the battery, how much energy per second is coming out of it. You know what I mean? And so the question is, what size external resistance will maximize the rate at which I'm drawing energy from that, will maximize the power, right? Does that make sense? That's the question, is what size resistance I hook up here that would maximize the rate at which I'm drawing energy out? So I'm trying to find the maximum power. All right. Now, I am going to tell you what the answer is, okay? You're going to go ahead, you're going to look. Viren has a video where he talks about maximizing the power from a battery with internal resistance, right? He's got a video where he goes through the derivation. You should watch the video and say, okay, I follow it, it makes sense, and then move on with my life. But just remember that the answer to the question at the end is a nice simple one. The resistance outside that will maximize the rate at which you draw it out is going to be when the resistance outside is equal to the internal resistance of the battery. So it's when R equals R. Okay, this is called matching the load. Okay, so when you match the load, that is going to drain the battery the fastest possible.